In this lecture, I want to talk about iterators. Iterator is a term that comes from the Latin word iter, meaning a journey or a walk. And essentially what the iterator is, in computer terms, is walking through or traversing a data structure. So the iterator is actually a design pattern that should be followed for every container class or data structure that you implement. The idea is a simple one. In fact, it's so simple that very often students struggle to understand. A lot of times they're looking for something that just isn't there. It's a simple idea. The iterator is a way to get access to each element in a data structure or collection one at a time. This design pattern offers a consistent interface, so it should be used for all data structures. Here's the iterator interface in Java. It has three methods: hasNext, next, and remove. hasNext is just the signal, it's a Boolean, whether or not there is another element in the collection that has not yet been returned. The next method returns the very next element in the collection. And finally, we have the remove method. In general, you should not implement the remove method. It really doesn't belong here. I think that this was added because of C++. That is to say, iterators are heavily used in C++, and they're used for a lot of different types of operations. They're used for insertions, removals, finding subsets of a collection. So they have a lot of functionality that are really part of the C++ language, but the iterators don't work this way in Java. And therefore, introducing in a very limited way some of the kind of functionality you might see in other languages strikes me as being a very bad idea. So in my sections when I teach CS310, I have students always just simply throw an unsupported operation exception for the body of the remove method in an iterator. Thus, what you really have are two methods: hasNext and next. So iterators then are a pattern for traversing a data structure in a systematic way. You start with the first element, return that, and then move on to the next. And so iterators return a reference or a handle to each element one at a time. The idea is really simple, and it's similar to a file cursor or a database result set cursor. That is, if we open a file for reading, we will read that file one line at a time. And so we will make a call to read line to get the next line. And when we do that, the cursor or pointer that exists in the file moves down to the next line automatically. That is, it starts at the beginning and then sequences through the file one line at a time as we retrieve it. So when you're reading a file, you don't have to do something like line equals read line and then move to the next line. You don't have to explicitly move to the next line. That is part of the operation. It is a cursor that automatically locates itself on the next element or item. And that's the same whether it's a file or reading result sets from a database or in fact reading the next element in an iterator. So iterators return one reference at a time, and they save state between accesses. This is the cursor idea. They know where they are and move down one at a time as you remove or access things in the iterator. Iterators support the do something with some or all items idea. So there are a couple of common things that we do with iterators that are listed here. The first is printing. If you stop and think about it, it makes absolutely no sense to put a print method in a linked list. Because when you write the linked list, you have no idea what's going in it. Then how in the world could you possibly know how to print what it might contain? Even if the objects going into the linked list have overridden the toString method in class object that supports printing, you still can't know exactly what you want. and in fact deciding or specifying how printing should happen inside a lower level data structure makes no sense at all. In fact, it's the application that needs to decide how things should print. Therefore, a data structure should never have a print method in it at all. There's just no justification for it because there's no way to specify what you should print. Therefore, the iterator is the mechanism we use to print what's in a data structure. You use the iterator to sequence through and print each item in the data structure. Similarly, you might want to update or search on the collection. And very often you're not looking for a specific item, but a set of items that match some criteria. So for instance, most data structures have a search method or search function, and it takes a parameter, what it is you're searching for. You're searching for X, and if you find X, you return it, and if you do the search and don't find X, you return null. This is a different type of operation where we're returning a set of things that match some specific criteria. So as an example of this, we might consider that we have a convenience store like 7-Eleven that has inventory items stored in a linked list. Then the boss comes to you and he says, okay, we got a price increase from Pepsi. So I want you to go through the inventory and I want you to change the price of everything from Pepsi, increase it by 10%. Well, without some way to access items in the linked list in a specific or methodical way, this would be an impossible task. One way you might approach this would be to edit the linked list code and add a new method, such as change the price. And in that method, which you would put inside the linked list, you go through the linked list and look at each item and see if it's a Pepsi object. If it is, you change the price, incrementing it 10%. Well, this is a really bad idea for a couple of reasons. First of which is you're putting Pepsi in the linked list. That is specific references inside the linked list code. But we don't want to do that. We want our linked lists to be completely generic, which means we can use them for anything. But they cease to be completely generic if we enter specific class information somewhere inside that linked list. So we don't want references to Pepsi or anything like that inside our linked lists. The second problem with that is adding code to do something that specific to a linked list is a bad idea. What happens if the boss comes back next week and says, okay, all of the products from Frito-Lay need to be increased by 7%? Then do you open the linked list code and add another method to increase the price of Frito products? Maybe you might come up with an idea of doing some kind of generic type of price increase thing. But again, this isn't really going to work because it won't be generic or general enough to apply in every case. Also, this breaks the concept of having reusable code. That is to say, you want to write your linked list once, have it completely thoroughly tested and vetted for correctness, and then you would never edit that code again, because if you open the code and edit it, you introduce the possibility of bugs. And so you no longer know for certainty that the linked list code is correct if you go in and edit it. So you don't want to do that. Thus, what you would do is use an iterator. You would get an iterator for all of the items in the collection. You would go through them one at a time. And you basically do this. You say, okay, first item, is this a Pepsi product? No. Next item, is this a Pepsi product? Yes, update the price. Next item, is this a Pepsi product? Yes, update the price. Next item, not a Pepsi product. Nope, don't do anything with it. Go on. Thus, you sequence through the entire collection, searching for the objects that are coming out to see whether or not they match a specific criteria. Because you're in the application part of the program, you know very well what you're looking at. So if you are pulling out products from the iterator, You have products in the application class. You can do the comparisons. You know what you're looking for. By the way, an important point we should probably add here. Sometimes students have the notion that they need to remove, say, an inventory item from the linked list, update it, and then reinsert it. But this is not really correct. This is not correct because what you get back from your iterator is a reference. So there's only one object that's on the heap with multiple references to it. The one inside the data structure itself, and then a second one that is returned to you, which you can use to update or change that object that is stored inside the collection without actually removing it and reinserting it. Java has two iterator design pattern interfaces, enumeration and iterator. Enumeration is the original class that was in the Java language from the beginning. However, at some point, I believe Java 1.2, they decided to introduce a new type called enum. Enumeration, of course, is a specific set of things. An enumeration means something like days of the week, Sunday through Saturday. There are 7 things. That's an enumeration. And so there was a conflict between the name and this new type they wanted to introduce into the language. So they came up with the iterator interface. So where things stand now, legacy code often uses the enumeration class, but all new code should use the iterator interface. So the iterator interface needs to be implemented in the data structure. That is, you have three methods that you must write, and they must be there or the class will not compile. So I want to take a look at some iterator code, and in specific there are 3 ways to create iterators that I want to look at. The source code that we're looking at here is for an array list. That is, a list, which is an abstract data type, implemented with an array. So we want to implement the iterator interface, and again there are 3 ways I'm showing you to do this. The first is to implement the array list, or implement the iterator rather, in the array list directly. As you can see here, I have public class ArrayList1 with the parameterized type E implements iterator E. So to do this, I actually put those 3 methods inside my ArrayList class. I also need to introduce something else, a new variable here, private int iter_index, and this is the index that keeps track of where we're at in the iterator. That is, we're going to start at index 0 and then move down to 1, 2, 3, 4, 5, and so on as we sequence through the iterator. So we have here the signature implements iterator E and then a new private variable iter_index to handle the index of the array that we're looking at in the iterator. So this class contains the standard methods for this array list, and here at the bottom I have the implementation for the iterator. So here we have public iterator E, iterator. So this is the method that gets called. Iterator returns an instance of iterator. This is the basic mechanism for doing it. Note what we have here, return iterator E, this. This is the current object, the array list that we're returning, but casting to type iterator E. This has the effect of masking off all of the methods in this class that are not in the interface iterator. Thus what we get back, the return from this method, is a reference that can only call methods that are in interface iterator. If we try to call the size method, for instance, using the return value of this iterator, we're going to get method not found error. So what we're returning is a linked list, but cast to, or not a linked list, but an array list cast to the type iterator. And then we have our methods. Has next. Well, if the iterator index is less than the current size, then there are more elements. So when we get to the stopping point, if the size is 10 and the iterator index is 10, there is no element at that index, therefore there are no more, and it would return false. Next. Here we return the item in the array and increment our iterator pointer or our iterator index. The remove method here you should always implement, or rather write this with throw new unsupported operation exception, just like this. There's no reason to implement this at all. A word about exceptions here. If there aren't any more elements, you don't want to return null and you don't want the program to crash. Therefore, part of the design pattern are the exceptions that you throw. In the case that someone calls the next method on an iterator that has no more methods, then you must throw a no such element exception. In the Java language there are a lot of exceptions, and many of them are quite long. This one is long, certainly this one, unsupported operation exception. But the reason for this is that they convey a lot of information, and the fact that you have thrown an unsupported operation exception means only one thing, that you've called remove. So they convey information, so it's important that you don't just throw some general exception, but that you throw specifically these. All right. Also, you must import Java Util Iterator and no such element exception. Now I want to take a look at the next way of doing it. So this first way, again, we implement iterator interface directly in our ArrayList class, which means we add those three methods to our ArrayList class. And then we return our iterator by casting this ArrayList to iterator, and that's what we have here, where we have our cast public iterator, iterator, return cast to iterator E, this. The second way of implementing the iterator interface is here, and this is probably the best way to do it. This is the preferred mechanism. Here what we do is we create an inner class inside our data structure. That is, inside of our ArrayList2, we actually write an inner class that is our iterator. So there are no changes to this class. We simply have added here at the bottom the array implementation. So here I have nested inside class ArrayList iterator helper. So this is buried inside. This is the closing bracket for the array list. So inside is nested the class iterator helper, which is an implementation of iterator. It has implements iterator E. Then we have, again, the standard method for getting an iterator from a data structure. We have public iterator E iterator. Return new iterator helper. We don't need a name for this instance. We could say iterator helper equals new iterator helper and then return helper, but that's not necessary. We don't need to have a variable. We just return new iterator helper, and it returns a reference to this class that's created by the keyword new here on the heap. This creates an instance of the iterator on the heap, and that reference is returned and used by the driver. So we have kind of a canonical approach here. This is the type of iterator that you can use for all arrays. Class iterator helper implements iterator E. So we have this initial value set to 0 for our iterator index. This marks the place where we're at as we traverse the iterator. And so the code in here is not really different. The only difference is it's in a named class, iterator helper. This has certain advantages over the first approach. With the first approach, you can only have one iterator at a time, because you're returning an instance to that class, so there's only one iterator index. So you cannot have two of them. Here you can. You can have as many iterators as you want, and each one of them will have their own distinct iterator index, which makes that possible. The other problem is that sometimes you need separate iterators in a class. And again, this becomes impossible if you have implemented inside the enclosing data structure itself. So this is the preferred way of doing it. There are certain changes that you can make in here if the requirements are different. For instance, if you need to return an array in sorted order, then what you would need to do is make a copy of the array in the outer data structure, sort it, and then use that copy here to return elements in sorted order. The next approach I want to demonstrate is using an anonymous inner class. That is, there's no real reason to have a specifically named class inside your array list. The syntax of this is somewhat less clear, and so you may prefer to stick with the second technique which we just looked at. But here's how you can do it with using an anonymous inner class. So again, no changes to the class itself. The only changes exist down at the bottom here where we're implementing the iterator. So the entire implementation is right here. We have a method called iterator that returns type E iterator. So the signature of this is your method, is precisely the same in all three of the implementations we have looked at. We have public iterator E iterator, and it does return the iterator. However, inside the body of this method is our anonymous class. So we have return new iterator. Notice that this is the only way you can actually have new iterator. Iterator is an interface, and so you cannot create an instance of an interface. What you can create is an instance of an implementation of it, but not the interface itself. There's no code there. Here you're supplying the code, so this is allowed. But notice this is the name of the interface, iterator, and this is the only place you can actually do this. Capital I, the class, which is actually the interface. So we have an open bracket here, and then we have the implementation. Our iterator index has next, next. The code here is just the same. The packaging is different. This is the closing bracket, and the semicolon terminates the iterator method. So this is the closing bracket here for our anonymous nested inner class. This is the close bracket for the iterator, and then down here is the closing bracket for the class. So here the code for the iterator helper is nested inside the iterator method itself. Any of these three methods are perfectly acceptable and may be used. However, second method here is probably the preferred best method. The third way of doing it is perfectly acceptable. And the first choice here, where we implement the methods of the interface directly in the class itself, is not ideal and probably should not be done. It's not preferred. Then we have a simple driver class that we can look at, and this is the way you access or use your iterator. So we have public class driver and then our main method. We're creating array list. I used ArrayList1. In this code, that will be exactly the same for any of them. So what I'm doing here is inserting at the end of the list the values 1 through 10. Then we get an iterator. Iterator, and the parameterized type is an integer. List.iterator. While iter.has next. While there are more elements in the iterator, print it. And then at the very end, outside the while loop, we have a blank line printed. So I want to run this, and it will do as you would expect it to do. And here we see 1 through 10. As expected, we inserted 10 things and we called our iterator. And so the way this works then, we get the iterator, which is a separate class with all of them except this first one. And then it cycles through this array one thing at a time, one object at a time, returning it. Note that this does not change the array or the underlying data structure in any way. Now we can do this with any of these and there's no change required in the code. So let's try this with array list 3. And the driver, as you can see, works precisely the same way. The next thing I want to talk about is fail-fast iterators. It's possible that the underlying data structure might change after an iterator has begun. In that case, the iterator is tainted and no longer valid. So in this case, the iterator must throw an exception rather than continuing to return elements. So as an example, there's no requirement that you have to put an iterator in a while loop and process the whole thing all at once. You might have a situation where it's part of a graphical user interface application and you have someone operating this application. They may want to, say, process 2 or 3 objects and then go answer an email or look something up and then come back to it. And you may have a situation where the data is multi-threaded. That is, you might have company records that are accessed from many different locations or by many people at the same time. So you have concurrency issues. So it's entirely possible that the iterator might become tainted because the underlying data structure has changed. If someone comes along and edits or removes an element from the data structure or adds another one to it, then the iterator becomes tainted, and in that case you should throw an exception. Fail fast means that the iterator should fail as quickly as possible. That is, the first call to the iterator after it becomes tainted should result in an exception being thrown. The way this is implemented, the way to do this is actually fairly simple. You put a counter in both the nested inner class in the iterator and also in the data structure itself. In the data structure, you increment this counter anytime the structure changes. When you create the iterator, you set the local counter to the data structure value, and if these two values are ever different, then the iterator has become tainted. So I want to add the fail fast to the code here so that you can see how this works. And I'm going to go and use this second implementation because I believe this is probably the best choice in the standard method of doing it. So here I want to add another private variable. Private, I'm going to make this a long, and let's call it modification counter. So we have a new class level variable, and this keeps track of the number of times the data structure has changed. So then I must initialize this in the constructor. So I'm going to put modification counter is equal to 0. Now, anytime the data structure changes, we need to increment this modification counter, which means all of the add and delete methods. So here's our add first. I'm going to copy this so I can just paste it for speed and efficiency. So here we have the modification counter we have added. Of course, we put it before the return statement. Peek just returns the element but does not modify it, so we don't need that. Notice too, before we go further, we have remove last here, but we've done modification counter plus plus. Occasionally students think that we should decrement this counter when we have a removal and increment it when we add something, but that's not the case. We always want to add it. We always want to increment it. So we have an add last, add first, remove first. Again, we always want to increment. Remove last. Peek first does not change the structure. Peek last does not change it. Here's another remove. Make empty. In this case, because we have made the structure empty, it makes sense to set it to 0. Contains does not change the list. Is empty does not change the list. Is full or size, none of those change the list. So we now have added to the modification counter and all of the methods that modify the linked list structure or the list structure. So now what changes do we need to make to the iterator helper? We need to add another variable here, long. Let's call it mod counter. So then we need to initialize the mod counter variable, but we're not going to initialize this to 0. Rather, we're going to initialize it to the value of our modification counter in the enclosing class, the ArrayList class. Mod counter equals modification counter. So we have given it the value that it has in the enclosing class, and then we're going to check and see if it changes. So in the hasNext method, we're going to put a test. If mod counter is not equal to modification counter, then the underlying data structure has changed and we have an error situation, a tainted iterator, throw concurrent modification exception. This needs to be new modification exception. So again, these exceptions are specified and part of the pattern, and you must throw exactly these: concurrent modification exception, no such element exception if you've run off the end, and then unsupported operation exception for the remove. Notice with the next, the first thing you do is check by calling hasNext. Therefore, if the iterator has been tainted and you call either next or hasNext, then this concurrent modification exception will be thrown. You'll also need to include this exception in your imports. Import java.util.concurrent modification exception. So this is ArrayList2. We want to use the one we have just edited, ArrayList2, to verify that the fail-fast iterators are working correctly. So there are certain changes I need to make. I'm going to make this larger, so I'm going to make the maximum value 100. Insert 10 items. Get the iterator. Now I'm going to remove the while loop. And what I want to do is print the very first element in the iterator. iter.next. All right, so let's compile this and run it. So what we expect to see here is the first element only, because we're calling it once rather than in a loop. And there's our 1. So this is doing what we would expect it to do. This is working as expected. So what I want to do now is change this code. I want to add another element to the list and then print. So list.add last 11. And then let's copy and paste the print statement. So we would expect a concurrent modification exception to be thrown because the list has changed after we have started the iterator. And here we see exactly what was expected. The 1 prints, but it's after the printing of the 1 that we actually taint the iterator by inserting the 11. And so here we have thrown a concurrent modification exception. Now you could put a try-catch block in here and go ahead and print your own custom error message rather than having the stack trace. That would be desirable and a good idea. Now I want to talk about the iterable interface. This is another part of this iterator pattern, but the iterable interface is a completely different interface. It's in a different file. All data structures that have a single parameterized type should use this. The iterable interface consists of a single method called iterator. So this is the method we have been using all along. This is the method that I have shown you, iterator, in the 3 implementations that we have looked at for our classes. And the reason you want to use this is for convenience. Here's the problem. Iterating over a data structure is messy. So the standard method, which we just looked at in the driver, you get the iterator by calling the iterator method. Then you have a while loop, or you could have a for loop if you wanted to. While iter.hasNext, and then you loop through and do something with it. Nested loops make the situation even worse. So I have copied this piece here from the Java documentation provided by Oracle, and I think this is a great example about how awkward and difficult using this standard method for approaching iterators is. So we have a nested situation here, and this is for a card game. So as you can see, we've got the note broken, no such element exception. What's wrong? So this code uses for loops instead of while loops, but the idea is the same. Essentially, we're doing a new card by iterating over suits and ranks and then inserting a card with each suit and rank. So this should presumably get us each of the suits and ranks. However, this has a bug, and so I've highlighted this in red. I.next pulls out the next item from the suit iterator, but how many times does it get called? Well, notice that it gets called for each pass of the inner for loop, the J loop. So if the inner loop goes, say, 13 times, then I.next gets called 13 times inside the nested inner loop. So I.next gets called too many times. That's the problem. This code can be fixed, and they have suggested a fix that follows, which is right here. Pull out the I iterator, the suit iterator, before you start the inner loop, and then don't call I.next inside this inner loop. Well, the point here is this is messy and ugly and something that a lot of people get wrong. And so Java has introduced a new mechanism for handling traversing iterators, and that is this iterable interface. What it allows you to do is to use the for each loop. So using for each loop, the code is changed as follows, and as you can see, we have nested for loops, but this is much, much cleaner. So the way to look at this, looking at the first example here for suits, for each suit in the collection suits do. This also works well with arrays. So this is a for each, and as you can see below here, for int I:(a). For each integer I, in the array A do. And so I is a different value for each pass of the loop. So from our 3.10 example, without the iterable interface, we have this code. This is the example that we looked at before. Iterator integer iter equal list.iterator, and then the while loop. But the iterable interface makes this very much easier for integer I colon list, system out println I. So this is the for each loop for each integer I in the collection list print I. This concludes our lecture on iterators.